Okay, thank you for the introduction. I am Christian Wimmer. I'm quite happy to talk to you today about the programming model of GraalVM native image, something that people informally call static Java, although of course it's not the best of all terms, but we will talk actually a lot about terminology and the programming model in this talk. Yeah, I have been working for quite some years on virtual machines. I have been I started my career sort of on the Java hotspot VM for a couple of years. I worked on SSA form, register allocation, and object layout optimizations. And I did a little detour into language-based security. And then since now more than 10 years, I've been working on a GraalVM. Has been a really fun decade. Started it as a small research project. We tried out a lot of things and finally got the whole project and also into production. And now it's a fully supported Oracle product. But what's even more important is it's open source. And it's also supported by a couple of other companies. So it seems to be really going well. At least that's what we see from our inside point of view. Always the beginning of every talk, kind of the same slide. I know it's getting old, but it's always good to repeat that and set the context, because GraalVM is three different things. First of all, it's a high performance optimizing just-in-time compiler. So you just replace your Java home with GraalVM and you get better just-in-time compiler performance. Then there's native image, the ahead-of-time compiler and the native image generator. And then there's this whole multi-language support. Maybe implement JavaScript, Python, Ruby, LLVM bitcode, WebAssembly, regex, many different languages, which is one of the most exciting parts of the talk. But from a research point of view, something that really interests me. But what I'm really going to talk about today is the middle part, the ahead-of-time compilation, native image generation. So for today, we are kind of about all of the talk, we are in the middle part. I will talk a little bit about trade-offs between JIT compilation and AOT compilation. But whenever I'm talking about something, assume I'm talking about the middle part of this field. What are my goals for this talk? What should you take home? First, I will introduce and explain the programming model of GraalVM native image. And yes, it is actually a pretty significant change to the programming model that you are used to from Java, from when you run Java on the Java hotspot VM. Then I'll try to convince you that this is a worthwhile programming model for Java. It doesn't come without downsides, but I think it has enough upsides to justify it. And then we'll look in some implementation details to see, well, where does this programming model, where does this closed world assumption help, and where does it hurt? First of all, of course, why would you even start with doing some kind of new programming model for an established programming language? And our goal is to kind of keep Java vibrant. As you probably all know, Java already turned 25 years old a few years ago. So it's pretty old and established programming language, but the world does not stand still. And so a lot has changed in the last 25 years. And actually a lot has changed in the last 5 years, I would say. And the cloud and microservices really changed how software is written. Like for the longest time, Java applications were this large, were deployed on this large application servers. It's like you had one Java VM running kind of your whole company's application or even the applications for multiple companies. But no more. Now we have switched to running as small things as possible, independent things that can be independently managed by the groups that actually write the software. Microservices are great, but as part of this new paradigm of writing software, new languages and ecosystems appeared. There's new languages like Go, there are new ecosystems like Node.js. And we at Oracle, of course, have the mission to make sure that Java actually keeps up with these new languages and ecosystems. But we, of course, don't just want to keep up, we actually want to be better than that. And I will try to convince you that Java can actually be better than Go for application startup and memory footprint. And I want to convince you that Java can have a better programming model than Go and Node.js. Yeah, with that, what is GraalVM native image? The kind of central question of this talk. And I'm spending quite a bit of time on that because my mission is kind of to correct Twitter and correct all of these, no, not all, some of even of our own marketing materials, because it's like, it's so easy to say, well, GraalVM native image is, well, an ahead of time compiler for Java. And it's like, well, what is native image? Think of it like GCC for Java. And I think from a conceptual point of view, that's wrong because surprisingly, ahead of time compilation is actually an implementation detail of GraalVM native image. Because what it really is more a snapshotting tool for Java. Think of it as CRIO for Java. So CRIO stands for checkpoint restore in user space, which is a pretty nice Linux tool where you can just snapshot the whole process and resume it anytime you want. So yes, GraalVM native image is kind of a snapshotting tool, but it's not a general purpose snapshotting tool, of course, because it's like you have very explicit control of the snapshot building. So it's like when you run the native image generator, what you're actually doing is you're starting up your application and you're initializing your application, and then you take a snapshot. And when you then really run your native image, you are kind of resuming that snapshot. So what GraalVM native image really is a new programming model for Java. And I like to call it application initialization at build time, because that really makes it clear. It's like you have two very separate phases, build time and runtime of your application. And at build time, you do far more than you were actually used to from other languages, from other ways to execute Java code. Of course, some shameless advertising. We have all the kind of research details about that written up in a OOPSLA paper from a few years ago. So you can kind of read the academic version of all of that also in the paper. So native image generation works as follows. You have your application with all of its dependencies, and including the JDK, and in our implementation also the VM itself, which is called Substrate VM. All of that written in Java. And then you really try to find out what of that application is reachable. So we run an aggressive points to analysis. But we not only find out what is reachable, we also run initializations of the applications. Important part of that is we run some initializations automatically when we can prove some initializations are safe. But as an application developer, you also have full control over that, so you can run your own application initializations at that time. So you as an application developer are free to run your user code during the native image generation. And as soon as you run Java code, you produce Java objects, and these Java objects are snapshotted, and you get kind of an image heap that is the initial heap that is automatically there when you start executing your application. And then, since data alone wouldn't help you, we also need to kind of put the code of your application in the native executable. So all the code that was seen as reachable by the points-to analysis is ahead of time compiled and put into the text section of your application. So that all of that works, you have one very important assumption, and that's the closed world assumption. So this points-to analysis needs to see all bytecode, all code of your application, because if you cannot do that, if you kind of have this open world, everything could be loaded at runtime approach that Java traditionally had, yeah, you cannot do any of these optimizations. But of course, since Java has such a long history, there is kind of a large part of Java libraries that, of course, use all the dynamic functionalities of Java, like reflection, JNI, proxies, also resources, kind of just load resources from a jar file. All of that we needed to support, of course, too, but you need to configure these things at image build time. So the central point is no loading of new classes at runtime. As always, there is no such thing as free lunch. If you want to get the benefits of GraalVM native image, then you have to restrict your application, and you are not allowed to do one thing, and this one thing is loading new classes at image runtime. And that kind of brings us back to that brings us back to kind of keeping Java vibrant. And why are we doing all of that? For the longest time in Java was kind of this loading of new classes in Java was kind of the central functionality of Java. All the big application servers kind of were based on this model. You have one application server running, and then you dynamically load in your application. The application server loads it and keeps your application running. And when the application is done, unloads everything. And it was a central feature of Java. But my point is that with microservices, there's absolutely no more need to load classes at runtime. It's even beneficial to not be able to load new classes at runtime, because every loading of new code is kind of a security risk. And if you have a kind of complete closed world assumption, you actually have security benefits, and you have performance benefits, you have auditing benefits. You can really say which code is running. So it's like, from my point of view, it's like, yes, we are taking a little bit away that Java developers were used to, but it is kind of a benefit to take that away. And the image sheet that is part of this snapshotting is kind of the central part of the programming model. I will talk about that a little bit more in detail. Because when you were traditionally running Java code on, for example, the Java hotspot VM, the only thing you did at build time, of course, is compile the source code, and everything else, loading classes, was done at runtime. And parts of your application, like loading a configuration file and running a workload, all of that is done at runtime. With native image, by default, of course, all the classes are always loaded at image build time. But as I said, the important thing is you can, as an application developer, do anything you want at image build time too. For example, you can load configuration files. And I have a pretty simple example for that, which I can call configure at build time and configure at runtime. So if you just have a little kind of hello world application that prints hello world, but to make it configurable, I actually don't just print hello world. I print something that comes from a configuration class. Well, it's like you have a handler, and we have a hello world handler, and that returns hello world, and that's the string that's printed. And of course, we need to configure our application, and we configure our application using a little JSON file that actually lists this class name. And in the configuration, here's my JSON file that says, well, that's the handler to be used, the class name hello world handler. And we use, in that case, a JSON parser to load that JSON file. All of that you can do with very few lines. That's the great thing about the Java ecosystem. There's a library for everything. And loading a JSON file, of course, is nothing more than 3 lines of code. And what's happening under the hood, of course, is like, then the JSON parser runs, it's using reflection, instantiates this handler class, and then you can run it. And all of that takes quite a good bit of time. So when I run this whole thing on hotspot, it needs to parse things, and I run that with perf to get time and instruction count. It's like, we have about 2 billion instructions, user space instructions to just load all of that and run hello world. When I build a normal native image out of that and do the configuration at runtime, then I need to do a few things. As I said, I need to make sure that I have my reflection support correctly configured. So I need to, ahead of time, configure and say, well, I need these 3 classes, or these 2 classes available for reflection. I need to be able to invoke this constructor. So I have a little thing configuration to do. I can do that in code. I can do that in a JSON file too. And it's the wrong shell. If I run this thing, I already built my native image. We see, of course, startup is much faster. You can start up in about 8 milliseconds, even when Zoom screen sharing is running, which always makes things quite a bit slower. And we are already down to the millions of instructions. And what happens here is like I get a binary out called configure at runtime. It's 18 megabytes because it contains all of the JSON parser, all of this code, and then loads the JSON file. Then I can say, well, why would I configure my application at runtime when I'm deploying a large cloud service on thousands of hosts, and they all want to use the same configuration? So why should I run all of this loading code all the time? And why should I even be worried about, well, is the correct handler being baked in my application? Is there maybe, instead of a hello world handler, also another handler like a prints the current date available, and something gets misconfigured, and then suddenly the wrong handler gets executed, and my microservice does the wrong stuff? So what I can do is I can use configure at build time, and there I can write my own so-called feature code. So I implement the native image interface feature, and I say, before the static analysis, I want to run user code. And before static analysis, I want to load my configuration from the file. This produces an object, one of these configuration objects, and I need to preserve it somewhere, and that's what we call an image singleton. You could also store it in a static field, but making it explicit is a little bit easier. So you just say, well, I store my configuration, and then at runtime, this code runs, and at runtime, you take this configuration out from the image heap, you look it up in the image heap, and you run the handler. So in that case, I already configure, I load my configuration file at image build time, which I have already done. And when I run it now, you see it runs much faster, and actually you get the same performance and the same instruction count as a real hello world, because there's really nothing dynamic anymore going on. Also makes the image much smaller, only 5 megabytes now, because, well, we don't need the whole JSON XML parser. It's like the static analysis does not see the JSON parser as reachable, so it does not include it into the image. So that's really the core part of application initialization at build time. It's like you can run whatever code you want and prepare anything you want, and then prepare things and at runtime, things are automatically available and loading is much faster. By the way, of course, these images all copy on write shared. So it's like you have a binary and the image heap is copy on write. It's like if you run start now many instances of this native image, then actually you get a good bit of memory sharing. Well, a nice theory works for my hello world, but does it work in practice? Yes, in the last year, last 1 or 2 years, many new microservice frameworks really embrace that, and Micronaut, Quarkus, Spring Boot, if you have heard of all of them, they really are making use of initializations at build time. And I have one tweet here as well. You have a full Micronaut microservice, and you also start up this complete service in 6 milliseconds. So it's not just that hello world now starts in single-digit milliseconds. You have real complete microservices that start up in single-digit milliseconds. Sorry, micro. But now back to our programming model. Why did we come up with that? And why not just do ahead of time compilation? First of all, of course, several just pure AOT compilers for Java existed. There's JAOTC, which used to be part of OpenJDK. Actually, with the latest version, it got removed again, which is using the GraalVM compiler for pure AOT compilation of Java. There was, of course, the GNU compiler for Java. There was Excelsior Chat, and but the main pain point of just AOT compilation for Java is like Java code is really hard to optimize without data. It's not like C code where code and data is strictly separated. Java code is just very object-oriented. And when you do AOT compilation, then you can only cover the code aspect of that, and you need to ignore the data aspect because you don't have Java objects. And in Java, you cannot even optimize very simple things like Java enums, because Java enums are objects. And if you don't have this object instance available, you cannot constant fold and optimize a simple comparison like, is my variable a constant enum? It's like, no, because you don't need to AOT compiling code that looks up, loads a static final field to get the enum instance and then does a comparison. So you actually would need to AOT compile in 5 or 10 instructions for a simple enum comparison, versus on Hotspot, the JIT compiler says, well, I'm just-in-time compiling for my current snapshot where the classes has been loaded and the object and the class is initialized, and I can just do a simple object comparison. That's why things like JAOTC, even though it was running in Hotspot using the same compiler that we are using for GraalVM native image, very trivial things like Java enum comparisons were far less optimized, and that means your code is running slow. And no one really likes code running slow, even when you start up fast. So my point is, to get to data, to Java objects, you just need to run parts of your application. There's no other way around it. One quick slide on terminology. Why do we call things native image and image generation? Lots of different terms have been used for this programming model, so I'm not claiming that we invented the programming model of application initialization at build time. As already said, snapshotting is a pretty common name for that. But for me, snapshotting focuses a little bit too much on the data aspect. And the same way, I don't like people to call native image an AOT compiler. I would also not really like them calling it a snapshotting tool, because it's kind of both. Other terms like staging, phase awareness are just too generic. Partial evaluation would be a good term, but for better or worse, we already claimed that the term for our truffle languages in the GraalVM, where we do partial evaluation at runtime to optimize JavaScript and Python. So that term was kind of unavailable. A frequently used term also is hosted execution. That term comes from the world of metacircular VMs, such as the Maxine VM and the Chikes RVM. It's like, yeah, it's hosted execution while you build something, and then you have runtime execution. We use the term internally quite a bit because we use kind of a lot of ideas and even a little bit of code from the Maxine VM. But in the end, we settled on the term image generation as the name for the build time. It's actually a pretty good term, consistent with Java terminology, because when you use JLink to just kind of get a reduced JDK, then they also use the terminology to build a custom runtime image. So we are kind of in sync with the Java terminology here. Now the important question is, well, what actually is the important part of the programming model, and what is just an implementation detail of GraalVM native image? So it's like if you would go ahead and start with a completely new implementation from scratch, which parts do you really need to keep, and which parts can you just do however you want and do differently? So from my point of view, the integral part is really the closed world assumption. Because if you do not know your entire application, you just cannot do aggressive optimizations. It's like you need to run a static analysis to find out what is reachable, and that requires a closed world assumption. So closed world assumption, static analysis, you need. You also really need the heap snapshotting, because as I said, without heap snapshotting, you cannot start up your application in Java quickly. And if you have all of that, then you actually can run your application code at image build time. And either implicitly when initializing classes, or explicitly based on triggers from the static analysis. Implementation details are, as already mentioned, AOT compilation, because in the end, you could use an interpreter and a JIT compiler as well if you want. So you could definitely build a version of a native image that actually, instead of machine code, contains still Java bytecode or any other kind of bytecode representation, and an interpreter and a JIT compiler. Would work, but of course, AOT compilation is kind of an important implementation detail, because it really contributes quite a lot to the fast application startup too. But in the end, Java has a long history with JIT compilation, and you could do that too with the same programming model. Which kind of static analysis you use is also pretty an implementation detail. We currently use a points-to analysis, which is kind of the more aggressive form of static analysis, because gives you for each variable really the exact types that can reach every variable. You could actually do a much simpler analysis, and here we have a research project to experiment with that. Just make a simple reachability analysis and see, well, what does that give you? The fact that we have kind of a runtime system written in Java, the part that's called Substrate VM, is also a complete implementation detail. I like writing code in Java. It's like, I think it's pretty good, makes many things easier if you have your runtime system and your application code written in the same language, because that allows inlining and cross-optimization. But in the end, if you want to build a VM in C or in C++ and then link it in, no problem. And also building a single self-contained executable is kind of a nice thing that we have, but not a necessity. So it's like if you build your application, like if you write your runtime system in C and then you link it dynamically with your application, or no problem, of course. Little bit of detour. Why do we actually have this thing with GraalVM? That's now GraalVM native image. As always, it's like we didn't really start out implementing exactly what we have right now. What we started out was actually implementing a very, very reduced runtime system that can run our GraalVM languages or the truffle languages, but can run them in a way that we can embed them. And you might have heard Oracle sells some databases, and our first goal was to run JavaScript in the Oracle database. That's actually a goal we have achieved, and Oracle database multilingual engine is available. If you use the newest version of Oracle database, just the stock product, you actually, it includes a native image of our GraalVM JavaScript implementation, and you can run JavaScript functions from SQL and call them from PL SQL. So it's like you have JavaScript as a first-class language integrated in the Oracle database. And this kind of first goal of running inside of the Oracle database really shaped a lot of the design decisions. At first, it allowed us to make many simplifying assumptions because, well, we wanted to run in one exact system, which is kind of its own operating system, and we control all code, so we don't need all of these complicated Java things like reflection and whatever, and everything needs to be initialized as early as possible, because the one thing that database people really don't want to give you is memory at runtime, because you want to have thousands and thousands of database sessions on one server, and so database people measure memory footprint still in kilobytes and not in megabyte or gigabyte. But once we had this very targeted, very narrow implementation, it was clear, well, now we can expand it because the fast startup and low memory footprint is useful for microservices and command line applications too. And so we expanded, but of course, real world code never followed all of our restrictions. And so now in the last so many years, we were on the quest, it's like, how much else can we support without breaking this initial benefits of fast startup and low memory footprint? So we kind of went from full applications written with this closed world assumption and expanded. And what really helped were these new microservice frameworks like Micronaut and Quarkus Helidon that came up. Then there were established frameworks like Spring Boot that were also able to kind of take benefit from it, because it's like they already were going in the right direction. But there is definitely a boundary. And it's like, just to make it clear again, there are definitely frameworks and applications that will never be suitable for a closed world assumption. So all of these traditional Java application servers, WebLogic, JBoss, just have dynamic class loading at its core. And so there's no point in trying to run these things as a native image, because that's not what it is designed for. One quick slide. There's always a little bit of discussion. Well, you talk about application initialization. Is that the same as class initialization? Is it something different as class initialization? For me, these two terms, class initialization and application initialization, are very much the same, because class initialization is just, well, you have static initializers. It's something that's built into the Java language from the beginning. But when you want to initialize your application at build time, of course, you need to initialize classes. And since class initializers are just Java code, you can do whatever you want there. So it's like, even if we would not give you kind of our special thing with image singletons, you could still just write very similar code and just run stuff in a class initializer and make sure you initialize the class at image build time, and then exactly the same thing happens. And but since, of course, we need to initialize classes, we inherit a lot of problems from this class initialization, because Java class initialization is a really tricky thing, and class initializers always have and trivial interactions. So that's why we came up with this complete separate API to say, well, you write the feature and this feature code runs at image build time. And writing this explicit code also has the advantage that we can actually give you at image build time very detailed access to the static analysis results. So it's like when you initialize the application at build time, you can implement hooks and say, well, I want to write code that runs only if a certain class is seen as reachable by the static analysis, or if a certain subtype is reachable, or if a certain method override is reachable. And you can also statically query these results. So you can, in your code, say, well, is this code already reachable? And if not, then you say, well, I don't need to initialize that. And you initialize things only when a certain class was reachable. That's a very important feature for frameworks, because it's like frameworks like Micronaut, Quarkus, they are pretty big. And you don't want to initialize your whole framework all the time. You only want to initialize the parts of the framework that an actual application really uses. And using this callbacks and these query methods, you can do that. A few examples, we go very quickly over that. Why is it good to run code at image build time? If you look at, for example, what Micronaut does, it's like they have synthetic classes to build some metadata that's actually generated code. It's generated code by the framework, allocates a lot of objects. Pretty clear just when you look at this code. There's nothing in this code that depends on any external state. You should just run this code at image build time, because you save a lot of time at runtime. For our GraalVM JavaScript engine, when you can actually save a lot of memory footprint when you run multiple JavaScript instances in the same on the same server, because I already mentioned that the image heap is shared by using copy and write sharing. So you actually can reuse all of these initialized objects from many processes, and you have the memory footprint only once. So it's like when you start like one JavaScript instance, you kind of, with GraalVM, you need kind of like 20 megabytes, but then additional JavaScript instances, you can actually start with only 500 kilobytes of additional memory. As I said, very important for running in the Oracle database, because it's like you just don't have the memory budget for each database session to allocate megabytes and megabytes of memory just to start up your JavaScript session. Another interesting use case is kind of this horizontal scaling of microservices. Instead of packing as much as possible in one process, you actually want to start many separate processes. And traditionally on hotspot, kind of the yellow bars here, it's like you start 4 VMs and you use 4 times as much memory as 1 VM. But with a GraalVM native image, it's actually you start 4 VMs and you only have 2 times the memory, because the image heap, all of your AOT compiled code, all of that is shared, and you really only have the very small new runtime heap in each process. So you get much better scaling when you start many processes for the same executable. Okay. That was kind of the talk about the programming model. Now for some implementation details. First, about static analysis. I have kind of a love-hate relationship with static analysis, because on the one hand, it really works great. And that was kind of the research part of GraalVM native image. It was like, first we needed to find out, is static analysis really feasible to find a small closed world for real world applications. And by real world, I mean, microservices that use a JDBC driver and that use all of these Java libraries. And the answer for that is yes, it works. That's the good news. The bad news is that the precision of the points-to analysis regarding the types that can really reach a variable or a field is not great. We have had some attempts to use context-sensitive analysis to increase the precision of the static analysis. Wasn't really that successful, so we didn't enable any of that in production. Instead, we actually are focusing on making the analysis faster and more scalable, even at the cost of a little bit of precision. But yeah, the really bad part about static analysis is, yes, you need to configure reflection, G9, all of these Java things at image build time. And we live with that. Also, reflection, of course, passes everything as object arrays. So it's like, as soon as you use reflection, you really, really hurt your static analysis precision. It's like, ground rule is like, don't use reflection if you don't have to. But also there's a solution. And in the last months, Micronaut actually released a very nice Micronaut module to do JSON serialization and deserialization completely reflection-free. And I think at some point I need to update my little application, because it would really help my hello world to get the checksum parser out even when you do the configuration file parsing at runtime, because with Micronaut you can do now all of these parsing actually completely reflection-free with much lower footprint too. I already mentioned security a bit. Closed world definitely has security benefits. You can have a software bill of material. It's like, you know exactly what is in your binary and nothing else will ever run. Don't want to hide here, of course, that snapshotting can also lead to new security problems, because you need to be careful what you do at image build time. If you access the username or the working directory or passwords or IP addresses or server names or anything at image build time and store that in the image heap, well, then you have that information in your binary. We do some checks so that, for example, the user directory does not get embedded, but in the end, you are responsible for that, because it can also be a benefit. I already said, it's like if you really want to deploy a highly already pre-configured microservice, then maybe something like server names and IP addresses you really want to hard and constant for, because you say, well, you're configuring your microservice for a certain use case, and then, well, if the IP addresses in your company are stable, well, you want them hard-coded and in the image. But if you put the native image on the internet to download, you probably don't want your server name in the image heap. One of the big benefits of closed world AOT compilation, and now I'm really going into the benefits of already the AOT compilation, which is not just a programming model, like you really have predictable performance. There's no de-optimization, no performance cliff. It's like, oh, the JIT compiler optimized something, but then something changed in your application behavior, and you just de-optimize half of your JIT compiled code and you started interpreter performance again. Cannot happen. The kind of 5 millisecond startup time that you have for your microservice is like what you have all the time, and the first request already runs with the full peak performance. And many things are really much easier when you have a closed world. For example, type checks. Don't have time to go into all of details of that, but it's like type checks in Java are tricky because you can have an interface, and if you do interface type checks, it's like, how do you do that? If you know the hotspot code, there are primary caches and secondary caches, and it's like, if you have a negative check for an interface, it's like if something is implementing an interface and you have many classes that implement that, and kind of something interface instance of this, instance of this, instance of this, it's very slow. On the other hand, with AOT compilation in our closed world, we can completely pre-compute all information necessary for type checks. There's a lot of math behind that with consecutive ones, properties of matrices. But in the end, the takeaway here is that's the little code part. That's really the whole snippet that runs for type checks. If you have an instance of with a constant class, then even this type here is constant. So the first 3 loads are constant folded, which means we can do a normal Java instance of with a fixed class with 1 memory load to load 1 number and then do a range check on that number. Guaranteed all the time. That's like if you do an instance of in native image, you know it's 1 memory load, always, nothing more. You can also do quite aggressive transformations of higher level operations. So to reduce code size, for example, we do outlining of allocations. Allocating a new object in Java is pretty big in terms of code size because you usually have a fast TLab allocation part and then a slow path to refill the TLab, and you invoke the constructor and everything. And for all the tens of thousands of places where Java code just throws a new exception, you don't want to waste that code size. And so we just outline allocations, and you actually get very small methods that do nothing other than invoking a factory method. For string concatenation, we can take the string builder plus operations, the append calls, and just outline that to type specialized concatenation methods. We also do a similar thing for string.format. When your format string is a constant, then we actually pass the string.format string at image build time, and you don't need to pass format strings at runtime anymore. And then you can do very aggressive object layout transformations, which brings me back to my old hotspot days, because object inlining and these things were actually my PhD thesis, and it worked sort of on hotspot, but it's like very difficult to kind of bring something like that to production, because on hotspot it's like, yeah, you always have to be aware that you load a new class, you need to de-optimize, you always need to be ready to kind of undo all of your optimizations. Versus, for example, string inlining in the closed world assumption is very easy. You take your string object, and you take the byte array, and you just combine it to one combined object. That's a hybrid of a string and array. And you don't have to worry about, well, what happens if, because if someone really uses reflection to access the string.value, so it's like someone really cheats and goes into the internals of the JDK, well, you know that already at image build time, and you can disable the optimization at image build time. So you can transparently say, well, you can tell the user, well, you should better not do that, but it's not a problem because it's like we can just disable the optimization at image build time, and but for most, or not to say all of the native images, we can combine the object there, the string object and the byte array. There are, of course, some challenges with AOT compilation. Java has precise exception semantics. Optimizing for that is quite tricky because you cannot really hoist anything, any null checks, any bounce checks out of loops. So there is a new set kind of compiler optimizations necessary to optimize for AOT compilation. The great thing about the GraalVM compiler is it's very modular, very flexible. So it's like, it's very easy to add these phases. And it's also not too much. It's like, you can say 95% of all your compiler optimizations just work both in JIT and the AOT compilation world. So it's like escape analysis, partial escape analysis, great method inlining, all of these phases, great, just work. But then you need a few targeted phases just for AOT compilation, like loop duplication, explicit loop invariant code motion to help with this precise exception semantics. And of course, JIT compilation phases like speculative guard movement that really do speculative optimizations, but it's just not necessary to run these phases when doing AOT compilation because they wouldn't find anything to optimize in the first place. We also must compile for the lowest common denominator of CPU features. For Intel, that's SSE2, maybe at some point AVX2. But again, the solution for this problem is loop duplication, method duplication. It's like if you have an important loop or an important method, well, compile them one version in the baseline and one version with full vectorization in case the hardware is available. So the same optimization phase that kind of helps you with the precise exception semantic to get the null checks and the bounce check out of loop. So then you already have kind of a fast version of the loop, and that fast version you can also compile with vectorization and CPU features that are not available everywhere because you always have the kind of slower fallback version that runs. It does all the guard checks and then also runs on old hardware. One of the biggest problems we are currently trying to solve is size of the AOT compiled code, because when AOT compiling everything, especially with method inlining, code size can really explode very quickly. And you really need kind of profile guided optimizations to only compile the hot important code for performance and the cold code for size. And how do you get profiles? Well, unfortunately, you never have profiles from your actual current application run. You always need to accumulate profiles from previous runs. But again, the deployment model is kind of microservices where you deploy many instances on many servers, and you change them frequently, you update them frequently, so you can kind of do sampling on all your servers, you collect the profiles, you accumulate them, and then every now and then you build a new binary that's then better optimized. One last topic, fun research that we have been doing in the last years. Actually not going through my slides here, but just going back to my little demo. It's like, yeah, configuration your application at build time versus runtime is nice if you do things at build time, but sometimes you don't really want to bake in your configuration completely at image build time, but you still want to kind of have a mostly stable configuration. And in that case, kind of persistent heaps are really good, because what you can do is like you can now have a third version of the application that loads your configuration at build time, but then once the configuration is loaded, actually writes out a little persistent snapshot heap with these configuration objects, so that subsequent starts of the application are fast. So we come back to my application here. When I started the first time, and so I really first delete my little configuration cache, and then I start my application at loading the configuration at runtime. I again get kind of the slowish startup with millions of instructions. But what happened now is like we loaded the configuration file, but we also wrote a little persistent heap file, 16 kilobytes. That is then an extension to the image heap, and that I can load at image startup. And when I run my application again now, then it loads memory maps in just this little persistent heap. And you see, you get kind of nearly the same startup performance again as what we had with initialization at build time. So it's like you kind of get the best of both worlds. You can configure your application at a runtime by loading a JSON file, but only the first time, and then subsequent runs are fast. And again, you get the same benefits for this persistent heaps that you have for the image heap. So you get copy and write sharing. If this thing would be larger than 16 kilobytes, if you have it in the size in megabytes, even hundreds of megabytes, you get a copy and write sharing of this persistent heap between your processes. So it's like a very nice extension that we did to this image heap model that really hopefully makes native image very useful. Also, for example, for truffle languages, it's like, well, you can kind of start up your JavaScript application, and then you kind of snapshot the whole JavaScript or Ruby application, and say with all the JIT compiled parts, with all the shapes, all the loaded source code, and you get one kind of snapshot image for your JavaScript application, and now you can start up a JavaScript application again, also again in milliseconds. Very nice addition to the GraalVM ecosystem. Also have it in the slides with all the numbers for load configuration at runtime, image build time, and with the persistent heaps.
Sorry, Christian, sorry to interrupt. We are,
Yep.
Is this
You're
your
out of time,
yeah.
And I'm done.
Yeah. I guess topic is.
That is my summary.
Yeah.
I leave that slide up, and
yeah, if there are
thank
any
you for your
questions.
time.
Yeah.
And I'm definitely also available in the breaks and everything if anyone has more questions.
Okay.
And we might have time for 1 or 2 questions now.
Yes.
Okay, thank you. And any questions?
So I didn't see any questions on chat. If anybody has any questions, please feel free to raise your hand. And the moderator will be able to unmute you. You can also enter them in chat.
Oh, yeah, that's the downside of virtual talks. Is like the question part usually is a little muted. But anyway, yeah, if anyone has questions later, feel free to ping me directly on the chat.
I would have a question. Actually,
Yes,
I don't have to raise my hand to get unmuted. So as I understood it correctly, for example, if I would want to write a front end for my language using this technique and then just hand out the binaries instead of people having to use a full-flexed JVM in order to run the front end, then loading a program that is going to be like parsed, then the program would in this use case here be your configuration file, or?
Yes, yeah. So it's like when I need to go back to my very first slide here, when about what GraalVM is. So it's like when you combine kind of the ahead of time compilation and native image generation with the multi-language support, which of course is entirely possible, what you then get is kind of a native image built for your JavaScript language. And so from that point of view, from the point of view of the native image generator, the JavaScript engine is the application. And so it's like the JavaScript interpreter and everything is built into the native image, and then you load your JavaScript program as kind of data. And yes, as you said, it's like kind of the JavaScript program would be the configuration. So it's like that's the thing you load at runtime. I hope that's
without having the specific program already at hand, just handing out the native image, so someone can like parse this program would not be possible, because then, for example, it's actually missing which all the classes that are being instantiated by for the AST and or.
If you mean if you have a Java application, well, if you do not put in this multi-language support, yes, then you need to know all of your Java code at build time. So there's like these are kind of the 2 different ways you can build a native image. So the normal way when people talk about native image is like, well, you know all your Java code, all of the code is built in, and then loading classes is not possible. So it's like you cannot just say, well, my Java class is kind of data that I load. That does not work.
Okay. Thank you.
Oh, there's a question. Have you explored compiling the Scala runtime with native image? Yes, so it's like Scala just generates Java bytecode, the Scala compiler. And so with With Scala code, it's like Scala code just runs as a normal native image and just works, because Java Scala code is just bytecode. There's also a research project, I think we are at the academic workshop here, to really interpret kind of and write the truffle language to kind of interpret the higher level representation that comes out of the Scala compiler. But that's not how people normally run Scala code.
And the second part, fully closed versus fully dynamic, is that?
If you just run Scala code as a native image, that's completely static. So it's like there's nothing really dynamic in Scala code. It's like, because it's just bytecode. And
okay.
Okay. Probably don't want to go too much over for the next talk.
So let's thank the speaker. Everyone can use your reactions. And thank you, Christian, for doing this early in the morning.
Thank you very much.
Yeah.